Everybody, we're going to put a close now on Chapter 8 by taking a look at Section 8.5, which is dealing with polynomial and rational inequalities. A polynomial inequality is an inequality statement that is defined by a polynomial expression and then some form of an inequality symbol. So we're going to come up to the board and we're going to take a look at polynomial inequalities first. And here's the first one that we're going to be dealing with. X squared minus x is greater than 20. Now the first thing that needs to be done to solve a polynomial inequality such as this one is to get all of the non-zero terms on one side of the statement and on the other side 0. Now we certainly don't see any 0 written up there. We do see a 20 written on the right hand side. And therefore the first thing that needs to be done is we need to move the 20 over to the left-hand side so that we can get a 0 over on the right. And so when we move that 20 over to the left-hand side, it's going to change its sign and we'll end up with this polynomial inequality. X squared minus x, move the 20 over and change its sign, greater than 0. Now we're looking at the standard form of a polynomial inequality. We have a trinomial on the left-hand side, we have our inequality symbol, and we have 0 on the right-hand side. Now, people, here is our objective of solving this inequality statement. We want to find all of the values of x that will satisfy this inequality statement. We want to find all of the values of x so that if they were substituted into this trinomial expression, the result would be greater than 0. For a result to be greater than 0, the result of this trinomial expression would have to represent a positive answer. It would have to be a positive evaluation for this to be true, because anything that is greater than 0 has to be positive. So I kind of wrote up here in a rectangular box here the word positive, because of what's going to have to transpire when we move in and solve this inequality statement. Now, the first thing that is going to help us identify all of the values of x that will make this statement greater than 0 are two things. One of the things that we're going to come up with is referred to as critical values. Critical values are going to help us define and solve this inequality statement. There's going to be another aid that's going to help us solve it, and that's going to be a number line. So let's move on to the next step so we can show you what we would then have to do. We're going to just temporarily, we're going to rewrite this statement as a quadratic equation without the inequality symbol. Just temporarily, just so that we can get what's referred to as our critical values. So we're going to bring down the x squared minus x minus 20 and just temporarily set it equal to 0. And now we're going to solve this quadratic equation by factoring. We make a couple of binomial factors. They each have to begin off with x. The sign of the last term is negative, so one of the binomials is plus, and the other one is minus. And we need to come up with two factors of 20 that when really subtracted from one another will leave us with a negative 1x, or a negative 1. So that would have to be a negative 5 and a positive 4. We then come down and we set each one of these factors equal to 0. X plus 4 is equal to 0. X minus 5 is equal to 0. And one of our values that we get for x is negative 4. The other one is x is equal to 5. These two values are called the critical values of this inequality statement that we've got. So we're going to take a number line and we're going to plot each one of these critical values on the number line. We don't need to show 0. We don't need to show any other values other than the critical value of negative 4 and the critical value of 5, which we have done. I put a little circle on the number line at negative 4, and I put a little circle on the number line corresponding to the positive 5. I did that for one primary reason. The negative 4 is a value that if substituted in to this quadratic equation right here, if we substituted negative 4 in here, we would get a 0 on the left-hand side. And if I substituted 5 in place of this quadratic equation, I would also get a 0. These two values are dividing this number line up into 3 intervals. This interval that is less than negative 4, this interval that is found in between negative 4 and positive 5, and the far right interval that would be all values of x that would be greater than 5. You see, going back to our original inequality statement, it is saying that x squared minus x minus 20 must be greater than 0. It has to be greater than 0. So the values of negative 4 and positive 5, they're values that make this statement equal to 0. And we can't have it be equal to 0. It's got to be greater than 0. So I put an open circle corresponding to negative 4, and I put an open circle corresponding to positive 5. Those open circles indicate negative 4 cannot be one of the values of x, and positive 5 cannot be one of the values of x. So the values of x are either going to have to be all of the values to the left of negative 4, all of the values that are greater than positive 5, or all of the values of x that would be found in between negative 4 and positive 5. So the negative 4 and the positive 5, they are the critical values on this number line that separate this number line up into 3 different intervals. Negative 4, I'm repeating myself, negative 4 and positive 5 are not solutions to the inequality at all. They're either going to be over here, in between negative 4 and 5, or greater than 5. So I'm going to erase this information right here. And I'm going to replace it by this statement. The quantity of x minus 5 times the quantity of x plus 4 has to be greater than 0. Remember, these came from when I said x squared minus x minus 20 equal to 0. We found our two binomial factors, and these two binomial factors led to those critical values that you see down there on that number line. Now, it's going to be this statement right here that's going to help us solve this given inequality statement. And when we solve this inequality statement, we're going to be asked to do two things when we solve it. The first thing is we're going to be asked to, or you're going to be asked to graph the solution on a number line. And the second thing that we're going to be asking of you to do is identify the solution using interval notation. So here is what we go through and do next. I've come over here on this right-hand side and I've recopied the two binomial factors. And I set it greater than 0. And the first thing that we're now going to go to and do is we're going to identify each of these intervals from this given number line right here. This interval right here has a high value of -4, and then it moves infinitely in a negative direction. So I'm going to come over here in this chart, and in this column that's entitled a test interval, I'm going to identify this first interval right here. The largest value is -4, and then it moves infinitely in a negative direction. So this negative infinity comma -4 will satisfy this interval right here. Then below that, I'm going to put the interval in the middle. It's all parentheses because there was no equal sign attached to that inequality symbol. We've got a -4 and then a +5. And then the third interval is +5 and +infinity. Now folks, just repeating myself here a little bit, we are not showing any of the values of x that satisfy this inequality statement. -4 is not a solution, but it is a critical value. +5 is not a solution, but it is a critical value. And what those critical values do, they split the number line into intervals. So the solution of this inequality statement is going to fall in either this interval, or this interval. It could fall into any one of them, but the critical values will help us do what we have to do. So let's go to the first interval, which is -infinity comma -4. And what we identify in this interval is we pick any value that falls in this interval. If you want to look back at the graph, we are not going to pick -4 because it cannot be a solution. So we'll pick another value in this interval like -5. And I'll just kind of note it right there. Now before we do the work for this one, I'm going to identify values for the remaining intervals so that they're already set up there. Let's go to the middle one. Let's just pick a random value of x that would appear, that would be located somewhere in between -4 and +5. We could pick -3, -2, -1, 0, 1, 2, 3, 4. We'll go ahead and pick 0. That is a very nice one to use. So I'm just going to stick 0 there. And then in the last interval, 5, +infinity, let's just pick the first integer that is greater than 5, and that would be 6. So we've identified our 3 test intervals, and we've identified our 3 values of x that we're going to pick. Here's all that we have to do. We're going to take this first x value of -5, and we're going to substitute that -5 into this inequality statement. Not this one. This would take too long. We're going to substitute it into this statement right here. And here's what's got to be true. When we substitute -5 in here and -5 in there, we're not going to be so concerned about what the values are going to be. We're going to be more concerned about the signs. We're only going to need to be worried about the signs, because keep in mind, whatever this value is and whatever that value is, when they get multiplied together, the result must be positive. Because this times this has to be a value that is greater than 0. And any value that's greater than 0 must be positive. So here's all the work that needs to be done. Let's substitute -5 in place of here. Let's just do this one first. And I'll put a little sign down right here. If you substitute -5 in place of this x, -5 added with another -5 is going to make that negative. It doesn't matter what the number is. It's going to make it negative. So I'm just going to kind of put a little negative sign there. That's going to represent the sign of what we would get for that little factor right there. -5 coupled with another -5 is going to make it negative. Put another parenthesis. Let's substitute -5 in this one. -5 plus 4, that's also a negative. Negative times a negative gives us this sign. That's the sign that we need. So we know right now, part of our solution set is going to come from this interval right here. Now let's go to the second one. We've already got our x value of 0. Let me get these ready. Let's substitute 0 in place of x. 0 minus 5, that's negative. 0 plus 4, that's positive. Negative times positive is negative. He is not going to be a part of our solution because the answer must be positive. Down here at the bottom, let's pick 6. 6 minus 5, that's positive. 6 plus 4, that's positive. Positive times positive, that's positive. From that chart, we can now show our graph and we can represent our solution using interval notation. So come down. Make that number line. Show those critical values. One of those critical values was 5. The other one was -4. That's where they were. Now let's show the graph. Okay? This interval right here, it gave us a positive. So the interval -4, -infinity, that is one of the solutions, part of the solution. So we make a parenthesis projecting in the infinity direction, and we shade. And we'll go down to this one right here. It can also be all of the values of x that are greater than 5. So make a parenthesis moving greater than 5 and shade the number line. There's the graph. And now the interval notation. Parenthesis, parenthesis, union, parenthesis, parenthesis, -infinity, comma, -4, +5, positive infinity, and this is what we're interested in seeing. That's number 1. Let's just do one other. Now let's go ahead and take a look at problem number 2. Okay? X cubed plus 3x squared is less than or equal to x plus 3. Now the first thing that we need to do is get it, so to speak, in standard form, so that this x plus 3 will be replaced by a 0. So bring down the x cubed, positive 3x squared, move him over, change his sign, move him over, change his sign, is less than or equal to 0. Now we gather a little bit more of an idea of what we're looking at here. X is allowed to be any values so that when everything is computed out, the end result must be less than or equal to 0. So the end result can be either 0 or negative. Cannot be positive. 0 or negative is going to be the response at the end that we're going to be interested in. So now we need to get our critical values so we can place those critical values on the number line and we can identify our intervals to test out. So the first thing that we do is we set this polynomial x cubed plus 3x squared minus x minus 3. We'll set it equal to 0 just temporarily so we can factor and get our critical values. Now we have a polynomial that consists of 4 terms, so we're going to have to factor it by grouping. So tuck the front pair, tuck the back pair, we'll plus sign in between. First grouping, pull out its GCF of x squared. That'll leave us with an x plus 3. In the second binomial group, pull out a negative 1. And that will leave us with an x plus 3 temporarily is equal to 0. Now let's establish our 2 factors. The greatest binomial factor, we pull it out, x plus 3. And the second one that we form is x squared minus 1, and that is equal to 0. Now as we survey those factors, we want to make sure that everything is prime. He is. He's not, because he represents a difference of 2 squares, which we are able to factor further. So bring down that factor of x plus 3. Do the difference of 2 squares to the binomial conjugates. X plus 1 and x minus 1. And now let's get our values of x, which will be our critical values. X plus 3 is equal to 0, or x plus 1 is equal to 0, or x minus 1 is equal to 0. X can be equal to a negative 3, or x can be equal to a negative 1, or x can be equal to a positive 1. Right? Now, I just want to erase just a little bit up here. Make a number line, and we're going to place on that number line these critical values. Negative 3, negative 1, and positive 1. And I come with sort of a different marker. Because the inequality symbol had an equal sign that was attached, and that the overall value of this can either be 0 or less than 0, for these 3 critical values, I'm going to put a darkened point there, there, and there. Those are all possible candidates for being part of the solution set of this inequality. Now, those 3 critical values have subdivided that number line up into 1, 2, 3, 4 intervals. One of those intervals is parenthesis, negative infinity, negative 3, and I'll put a square bracket right there, not a parenthesis, but a square bracket. A second one would be the values in between -3 and -1, including -3 and -1. So we'll put brackets. A third one would be -1 to +1, brackets. We will. And then the fourth one, the smallest value can be 1 and going to a positive infinity. So there's are the 4 intervals. Now placed up here, I'm going to write down the actual inequality statement using the factored form that we came up with. Not this one, but this one right down here, and just kind of change it to this way. The quantity of x plus 3 times the quantity of x plus 1 times the quantity of x minus 1 must be less than or equal to 0. So we're going to pick a value from each one of these intervals. Let's start with this one. Let's go ahead and pick a -4 that would be found in this interval. Let's go to the second one. In between -3 and -1, let's pick a -2. For this third one, in between -1 and 1, 0 would be found in there. And the fourth one, any integer that would be greater than 1, let's go ahead and pick 2. Now, I'm going to get the little quantities kind of set up right here. I'm going to put 3 of them in here. And what we're interested in is a sign that's going to be negative. We've already accounted for the 0. The brackets are already up there. They've accounted for the 0. We need a negative response. That's what we need as we go through it. So let's test -4. -4 plus 3, negative. -4 plus 1, negative. -4, -1, negative. If you are multiplying together an odd number of negative factors together, it's negative. So he's going to be part of our solution because he's negative. Let's go to this interval, -2. -2 plus 3, that's positive. -2 plus 1, that's negative. -2 coupled with another -1, that's negative. Negative times negative is positive, and positive times positive is positive. That one's positive. That interval is not part of our solution set. Let's go to the third interval, 0. 0 plus 3, that's positive. 0 plus 1, that's positive. 0 minus 1, that's negative. Positive times positive is positive. Positive times negative, negative. This interval is going to be part of our solution set. And then finally the last one, let's test out 2. 2 plus 3, 5. That's positive. 2 plus 1, that's positive. 2 minus 1, that's positive. 3 positives, that's positive. So they're out, he's out, he's out, and these two are in. So let's see if we can handle the graph right up here. Part of our solution set is going to be the interval -∞, -3. Now, we make a bracket. We shade. And the other one is -1, +1. We make a bracket pointing to the right and a bracket pointing inward to the left, and we shade in between. There's the graph. And now the interval notation. Parenthesis, negative infinity, comma, negative 3 gets a bracket. Begins with a bracket, negative 1, ends with a bracket, positive 1. This is the solution. This is what we're wanting for number 2. Right? Now let's move to the rational inequalities. And show you how this is going to go. Okay, it's a rational inequality. You can see that it is because the expression on the left-hand side is a rational expression. Now, it too must be written in standard form. You must have one and only one rational expression on the one side, and it must be whatever the inequality symbol is, and 0 must be on the other. It must strictly be one rational expression alone, let's say on the left-hand side. Now, here's the unique characteristics about how we obtain the critical values for a rational inequality. First of all, before we go to the values, x is allowed to be any value, so to speak, with one exception. We'll talk about that one exception in a moment. I'm just kind of making a general statement here. The value of x can pretty much just about be any real number so that the end result has to be less than 0. For the end result to be less than 0, we're going to be interested in a negative sign at the end. It's going to have to be negative. Now, here's the nice thing about the rational inequalities. There really isn't any factoring that needs to be done because our critical values that we can obtain from this rational inequality are found by setting the numerator equal to 0 and setting the denominator equal to 0. Let me define each one of them. When we set the numerator expression equal to 0, that value that we will obtain will be the x-intercept. That'll give us the x-intercept. That will give us one of our critical values. So we're going to take that x minus 5 and set it equal to 0. Or we're going to take the denominator expression and set it equal to 0. What is the denominator expression? What is it defined to be? Its solution that we'll get when we set it equal to 0 will be the value that will make this fraction undefined. That's the second critical value. X minus 5 is equal to 0. This will give us the x-intercept. X plus 2 equaling 0, the value of x here will give us the value that will make that fraction undefined. So x is equal to 5, or x is equal to negative 2. Make the number line. One critical value, negative 2. The other critical value, 5. Here's a key little item. Folks, I'll say this carefully and slowly. The denominator expression. This is the expression that leads to the value of x that will make that fraction undefined. the value that we get for the denominator, x is equal to -2, he will never count. He will always get a 0. He will never count. Even if there was an equal sign attached up here, the value that makes the fraction undefined, he can never be that value. X can never be -2. And he's not going to be 5 either because there's no equal sign attached. If there would have been an equal sign attached, he would have gotten darkened. He stays open. But he's going to be open as well because there's no equal sign. Okay. Now, we've got our 3 different intervals. Let's identify this interval. Parenthesis, parenthesis, -∞, comma, -2. The second interval, parenthesis, parenthesis, -2, comma, 5. The third one, 5, positive infinity. Let's pick a value. Let's pick a value from this first interval, like -3. Let's pick a value from this middle one, 0. Let's pick a value from this last one. Let's make it 6. Now here's what we're going to need. We need a negative sign. So let's just copy this problem right here. X minus 5 over x plus 2 is less than 0. And let's give it a check. Again, we need a negative sign. Let's pick x as -3. -3 coupled with a -5, that is a negative. Divided by -3 plus 2, that's a negative. Negative divided by negative, that's positive. That is not going to contain our solution. Let's go to 0. 0 minus 5, that's negative. 0 plus 2, that's positive. Negative divided by positive is negative. He's part of our solution. The last one, let's test 6. 6 minus 5, 1. Okay, that's positive. 6 plus 2, that's positive. Positive divided by positive is positive. This is the only interval that will satisfy the solution. So we'll come over here, and I'll try to do it right in here. This is the only interval that will satisfy the solution. So you make a parenthesis there, and a parenthesis there, and you shade, and then the interval notation would simply be -2, comma, +5, and we'd have that given solution right there. Now there's one more that has to clearly be shown, and then we'll be done with 8. All right. Just erase it and we'll get it up there. Call it number 4. And number 4, 2x over x plus 1 is greater than or equal to 1. Now this is probably the highlight problem. We don't see a 0 over there on that right-hand side, so that 1 is going to have to move over to the left. And remember, when it gets moved over to the left, we're going to have to compute with the left because we can only have one fraction on the left-hand side. So let's get it set up first. 2x over x plus 1. Move him over and change his sign. Minus 1 is greater than or equal to 0. In the box right here, before we go any further, the values of x that when substituted into this, the end result being greater than or equal to 0, it can be 0 or positive. So the positive sign is going to be the key item. Now, on this left-hand side, we have to simplify this expression on the left-hand side to get it down to one fraction. So I'm going to temporarily write that minus 1 over 1. And we're just going to subtract these two little fractions right here, and I'm going to kind of pull it off maybe to the side a bit. 2x over x plus 1 minus 1 over 1. Let's find a common denominator. The common denominator would definitively have to be x plus 1. Put it under both. Now let's rename. X plus 1 theoretically divides into x plus 1 once, and 1 times 2x, that's going to remain the same. 1 divides into x plus 1 times, and x plus 1 times 1 will give us an x plus 1 written up there. Coming down, we've got a common denominator of x plus 1, and very carefully here, it's 2x minus the quantity of x plus 1. I'm going to kind of stick a little distributor there. That would be 2x minus x minus 1 over x plus 1. And that's going to lead us to x minus 1 over x plus 1. We'll transfer that singular fraction right up here. X minus 1 over x plus 1 is greater than or equal to 0. Now let's identify our critical values. The expression in the numerator will give us the x-intercept. X minus 1 is equal to 0. X is equal to 1. The denominator expression gives us the value that makes that fraction undefined. X plus 1 is equal to 0. X would be equal to a negative 1. Number line. Let's place negative 1 there. And let's place positive 1 there. The negative 1 was the value that makes the fraction undefined. He cannot be negative 1. So he's going to get a circle. However, the x-intercept of x equaling 1, he can be 1. He can be that. He can't? He can. The equal sign is attached right there. So now let's look at our intervals. Just kind of improvise here a little bit. First interval. A parenthesis, negative infinity, negative 1. Second interval. A parenthesis, he can end with a bracket, and he'll be negative 1, 1. And the third, he'll begin with a bracket, he'll end with a parenthesis, 1, positive infinity. Let's pick a value that would be less than negative 1. Negative 2. Let's pick a value that would be found in between negative 1 and positive 1. That would be 0. A value in this third one, that could be a positive 2. Right over here, we'll transfer this fraction. X minus 1 over x plus 1 must be greater than or equal to 0. We're interested in a positive sign. That's what we need. So let's test negative 2. Negative 2, negative 1. That's a negative. Divided by negative 2 plus 1, that's a negative. Negative divided by negative, positive. He's good. Let's test 0. 0, negative 1, negative. 0, positive 1. That's positive. Negative divided by positive is a negative. He's not. This one, let's test 2. 2 minus 1, positive. Divided by 2 plus 1, positive. Positive divided by positive, positive. Good. Let's go to the graph. We can pick this interval. He's going to get a parenthesis projecting to the left, and we'll shade this one. He will get a square bracket, and we'll shade, including the arrowhead. And now the interval notation, parenthesis, parenthesis, union, bracket, parenthesis, negative infinity, comma, negative 1, positive infinity, and there would be the entire solution for that inequality statement. Puts a close on 8-5, and it puts a close on Chapter 8. Kind of a rush game. That's what it's been about. Thank you. Goodbye.